Let's look at electric field lines for parallel plates. Earlier we have looked at the field lines for a point charge and also a point charge with other point charges, and we also look at a case of point charge to a plate. So in this case we are going to look at two parallel plates. It consists of two conducting plates, which is conductor, that is having equal and opposite charges. So its field is going to look like this. Okay, so you need to draw this on your handout. Okay, so from the positive plate to the negatively charged plate. So again, the direction of these field lines, same thing, it indicates the flow of a positive charge. Okay, so if you place a positive charge inside there, it will move from the positive plate to the negative plate following the direction shown by the arrows. Okay, so I'm putting these two cases side by side. One is this uniform electric field, and the other one is the non-uniform electric field. Okay, uh, the field lines it will be slightly different if you look at them carefully. Okay, so I want you to identify the difference between these two types of field. So take a second, take a minute to identify some differences, and then you jot it down. Okay, you pause the video, you view it, you find the differences between these two categories, and then you replay it. I mean, you press play and to see whether your guess is right. Okay, so I hope you have found some differences. That the first thing is you can see those few lines on the right hand side here. They are like very curvy. Okay, their distance between the lines, the distances between the lines are very irregular. And then on the left hand side here, where we have the parallel field, the distance between the field lines is even. Okay, distance between the field lines is even. You can see all the differences here. They are actually equal. Okay, it should be drawn in such a way. Okay, because this is a uniform field, so the evenly distributed or evenly spaced line indicate that this is a uniform field. So what is the significance of this uniform field? Later we're going to talk about that, but you can already have some guess, as in, because earlier we mentioned that spacing or density of the lines actually indicate how strong is the field. So if you have evenly spaced line, means that the strength inside here is actually the same everywhere between the region of these two parallel plates. Okay, whereas those here they are not equal if you draw the same circle, size of circle within the region of the two charges in this example. So their density is slightly different, indicating that it's not a uniform field. All right, so let's move on. Since we are talking about field strength, there is a quantity that you must understand about it, okay, which is called the electric field strength. It's a quantity. And how do we define that? Is force per unit charge at a point, field strength at a point, let's say this point. Okay, is defined as force per unit charge on a small positive charge placed at that point. So at this point that I indicate here, there's a field strength E. Okay, what does that mean? Is that it means if I place a positive charge there, I calculate the force divided by its charge, I will get the field strength there. Or the other way around is that if I want to find the force acting on this charge, positive charge, I want to find the force acting on it. So what I need to do is I will just need to multiply the field strength by its charge. Okay, because it has so much that much of charge, then I multiply by the field strength at that point, then it will become its force. Okay, so my assumption just now is the charge is the source of the field is a negative charge, so by right is a positive. never mind, just ignore the diagram that I drawn just now. Okay, so we can take on this positive charge. That's the same thing. So, but this is looking at this point here, this point, then there's a positive charge there. So equation y is E equals to F over Q. Okay, that Q is a positive charge. All right, so if you look at the equation, like I said just now, if I want to find the force acting on the positive charge, I just need to move the Q over there, as in I multiply its charge to the field strength there, then I will get the force that is acting on it. Okay, because it's per unit charge. So if I put 10 times of the charge, then it will be the force will be 10 times. If I put 100 times of the charge, then it will be 100 times the force compared to just the field strength. And the unit is Newton per Coulomb. All right. So let's look at uniform field. So just now we are talking about a point charge, the field strength around a point charge. Okay. So now we talk about a uniform electric field. Uniform electric field, as we mentioned just now, it is the equally spaced everywhere, and therefore the strength is the same at any point that you pick inside the field. Let's say I want to pick this point. I want to find the field strength here. I want to find the field strength here, field strength here, field strength here, field strength here. So I will get the same value. The value of the field strength is the same. It's similarly strong everywhere. Okay, so there comes another equation that governs this field strength. V over D. So V is the potential difference between these 2 points. Okay, let's say it's 5 volt. Okay, the potential difference between these 2 plates is 5 volt. Okay, then the V is 5. Distance D. So that's the perpendicular distance between these 2 plates. So if let's say it's 5 mm, then the D is 5 mm, you convert to meter. So E is field strength, V is potential difference, and D is separation. And the unit is V over M. Okay, V over M. So which means that this V over M is the same as the Newton per Coulomb just now. Okay, Newton per Coulomb. They are just equal. Okay. So having said that, if I put a charge inside here, let's say I put a positive charge inside here, and I want to find its force at this point, and then I place it at another place, this point, so you will definitely get the force to be the same, because the E is the same everywhere, and therefore if you apply the equation just now, this E is the same everywhere. So if you place at different points inside the field, the E is going to be the same and the charge don't change. So the force that it experiences is going to be also same at every point inside the uniform field. Okay? And if you want to talk about the acceleration, of course its acceleration is going to be also the same, because F equals to ma. Okay? So let's look at one example here. We have 2 parallel plates and separated by 0.14 meters, and its potential difference is 28 volt. What is the field strength? So it's a very direct application, V over D, and you should get the answer. Okay. Secondly, force on the 2 nanocoulomb charged particle placed between the plates. So we can use the equation of F over Q. Remember that F over Q is not just for the point charge in the space. It also can be used to calculate field strength inside uniform field. Okay, it's just that uniform field has another equation, E equals to V over D. All right. So we can use that and multiply the charge with the E. Q is 2 times 10 to the power of negative 9. Nano is 9, negative 9. And times 200. Okay, then you should get the answer. Okay, so we go for one more example. So we have this 5 cm. Here is 0, yeah, 0 volt. So two closely spaced metal plates connected to 500 volt. Draw solid lines to represent the electric field between the plates and add arrows to indicate the direction of the field. Okay, so it will be evenly spaced lines, and this will be your assignment question. So you need to submit this. And it continues to the next part. Okay, if an electron is placed in between the plates, find the force on the electron. Okay, so again, you can use the equation of F over Q as a hint for you. All right. So there's another question after that, after the previous one. Uh, you need to find the force on a proton that is placed inside the uniform field. Okay, so this one will be also your assignment question. All right, I will see you in the next video.